And hi, welcome. So today I'm going to try and verify the thermodynamic equations or state. Okay, so I'm going to take data from Senjal's thermodynamic books, the steam tables and the critical properties of water. Okay, these are the pieces of information I'm going to be taking from there. Okay, so let's just begin. Apparently, I'm having some bibliography problems. Okay, now it's okay. Yeah. So, where was I? Okay, yeah, I'm going to have us some test cases for finding molar volume. Let's just put the equations right now. Okay, or the pieces of data. Okay, so what are the critical properties of water? Okay, and I'm going to use the Peng-Robinson equation of state to calculate the vapor volume at a certain temperature and pressure. So water, critical properties. Okay, so mass, no, temperature. I'm just going to put TC here. T critical. Okay, I'm going to have to put them in quotes. Let's see whether this turns out right. Okay, I don't need the brackets there. T critical equals to how many Kelvin? 647.1. 647.1. And actually, I'm not going to put the Vim keys anymore because I've heard some feedback that it was quite confusing. So I'm not going to use it anymore. So just bear with me as I type. Okay. For water, T critical is this much. Okay. 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 So T critical for water is this much. What's the pressure? Okay. P critical is 22.06 megapascals. Okay, I'm just going to do it like so. Okay, here are the properties and the critical volume. Actually, yeah, maybe this is a good I don't need to use steam tables after all. I'll just use this as the critical point. I'll use this as a test for the Peng-Robinson equation of state. So the critical properties of water are 647 T critical. The critical temperature is 647 Kelvin. Critical pressure is 22.06 megapascals. And the critical volume is, let me see, 0.0560. And here's the units, meter cube per kmol. Okay, meter cube per kilomole. All right, so that is these are the critical properties, and that is going to be perfect for use in this test. Okay, so uh, this is what I'm going to do. I'm going to make a test for the vapor vapor like roots. Okay, so I'm going to make a test here. Okay, the function is called a crit point water test. PREOS. So name your tests name them like so. Okay, I'm going to make a new terminal, and what I'm going to do is I'm going to do cargo watch -x test. Okay, the test passed because there's nothing to run here. Okay, so what are the critical temperatures, pressures, and all that? Okay, it's 647.1 K, 22.06 MPa, and 0.0560 meter cube per kilomole. Okay, it's per kilomole. Okay, and let me just do a citation first at Senjal. Okay, Senjal. Alex Sangel. Okay, let's see. Okay, that should do it. So this should be help us yeah, do the citations, right? I just want to make sure I cite correctly. So again, with every test we have expected behavior and intended behavior, expected behavior and actual behavior. So this is the expected behavior. Okay, so let water create temperature. Okay, goes thermodynamic temperature new, and what it's a Kelvin 647.1. Okay, let water create pressure equals to pressure new megapascals, I guess. Okay, megapascals 22.06. I'm just going to use the units as such, and I'm going to add this to the use this unit. Okay, I'm going to use this unit. What else am I going to do? I have a critical volume. Okay, I'll need to underscore here, equals to volume new. Okay, new okay, I should use molar volume, not volume. Molar volume new what is this meter, cubic meter per kilomole. Let's see whether this exists. 0.0560. Okay, cubic meter per mole. Okay, let me go and find this online to see whether yeah, right, here it is. I'm going to go UOM. So pardon me, skip this part if you get bored. UOM Rust GitHub. Then we can see what units there are. What units there are. So I'm going to go to source SI, and let's go to molar volume. Molar volume, here we go. Molar volume. Okay, so cubic meter per mole, cubic decimeter per mole, cubic centimeter per mole. Okay, so everything's in a per mole basis. It's not a per kilomole basis. So I guess I'm going to have to do some, what do you call that, manual conversion. Okay, so 1 kilomole is going to have this much. So 1 mole is going to be 1000 times less. Okay, the volume is going to be 1000 times less. I'm just doing it like this. Okay. Okay. So why is that mismatched type? Oh, expected F32. Arguments to this function is incorrect. Oh. I see. I got to delete this. Okay. I've imported the wrong things. Okay, that's the thing. Basically, the UOM crate has two types, two main types you might bump into. There are more than that, more than those two types, but there are the F32 and F64 type. That is the double floating point and the the normal floating point, which is 32 bits versus 64 bits. I happened to import the 32-bit one by accident, so yeah, that's what happened. Okay, let me clean up those unused imports. Okay, I'll save it. I need to tidy things up. Okay, so I'm going to use all this. Oops. Yeah, for tests, it's better to import. Okay, it's better to import your the specific things you use for the tests, the modules, functions, whatever you call them. It's better to import them within the test itself rather than in at the top of the file as you saw. So these are what I want. Okay. OpenFOAM C F64. Okay, and then I'll have all of these items here. Okay. Let me do some more debugging. Okay, pardon, there's no F64 here. There you go. So if you want to import multiple things, you have to use this syntax. Okay, use UMSI. If you want to do multiple, just have them all in the brackets. I prefer to separate them. Okay, if possible, but this makes it a bit longer, but it's slightly more legible. Okay, let me remove the brackets, and there we go. Here, so we have the critical pressure, temperature, and volume. So, well, since we have that, let's use the Ping-Robinson equation of state, okay, and find the volume. Okay, find volume using Ping-Robinson equation of state, and it should be able to yield the correct answer. Okay, so this is me testing. So every time I add a new layer of complexity, it's always a good idea to test. Okay, so let's test the vapor root function. So get molar volume, Ping-Robinson vapor-like roots. Okay, I'm gonna do that. Where's my test? And as you see, the file is getting more and more messy. So it's probably a good idea to start splitting up the files, but probably I'll do that later. Okay, so let water volume, vapor volume PREOS equals to Ping-Robinson equation of state. Find the vapor-like roots. So there are a few things here. Okay, I need to put in the eccentricity factor, critical temperature, critical pressure, so on and so forth. So the pressure is, okay, I'm going to put here, set the input parameters for the function. Let pressure, so the pressure in question will be the critical pressure. Let crit pressure equals to water crit pressure. Let temperature, okay, let temperature equals to water crit temperature. Let crit temperature equals to water crit temperature. Okay, so there's one more, is the eccentricity factor, which I will need to find. So just give me a moment. I'll need to go and find this out. Well, the eccentricity factor of water. Okay, so I found the eccentricity factor from another textbook. It is not Sangel's textbook, Sandler's. I used Sandler's textbook. So let me do that. Okay. The eccentricity. eccentricity factor. Okay, spelled with one C, yeah? Eccentricity. Okay, I'm just replacing all the spellings because I spelled it wrongly the last time. Eccentricity factor of water is, okay, this is it. Omega, I don't need that anymore. Omega water equals to, and it's dimensionless, yeah, dimensionless, 0.344. Okay, and let's take a look. Is it done properly? Yeah, now it should work. Eccentricity factor is known as omega. Okay, yeah, it's just called omega. So what's the eccentricity factor? 0.334. Eccentricity, and again I spelled it wrongly, eccentricity factor. Let me change this. Okay, it's spelled with one C because it's acentered, not accented. Eccentric. Eccentricity factor equals to 0.344. Okay, so that is the eccentricity factor of water. Okay, and it's expecting a quantity. This is what I must write. And that should compile. Or not. Okay, what is missing? Yes, get kappa eccentricity factor. Okay, let's look. Get kappa eccentricity factor. Okay, that should compile now, right? And let me just do a few more things to tidy things up. Okay, I'll just change the spelling as such. So just hold on for a while. Let me change all of this to the eccentricity factor. Okay, eccentricity factor. Okay, no more ACC. Actually, I should have used the find and replace throughout the whole text, but never mind. Yes, here's the eccentricity factor. Where is the test? Here it is. Okay, so now I have a water vapor for the Ping-Robinson equation of state. I have this molar volume, right? This should be a molar volume. Okay, so now I will assert assert them approximately equal. Assert approx equal to within maybe 5%. Maybe to within 5%. I'll just do 5% first. I'll try to go as small as I can. Okay, so what am I doing here again? I have water critical volume data, which is tabulated, okay, from thermodynamics textbook, and I am using Ping-Robinson equation of state to get the water vapor volume. These are molar volumes, okay, given the critical temperature, pressure, and so on. So if these two match within a certain error, I think this code is working pretty okay. So this is at critical point. Okay, so let's try that. For this, assert approx equal should work. Assert relative equal. Okay, vapor molar volume and water crit volume. Okay, and max relative equals 0.05. Let's see whether this works. Okay, it says the trait bound does not satisfy Okay, the relative equal is not satisfied for them. Okay, so basically I'll need to so-called use the get method, and I will basically need to convert both of these into a float 64 type. Those are okay. So I'm actually just converting these quantities into float 64s. So get I need to supply uh, the units cubic meter per mole, and that will do it. Okay, cubic meter per mole. And I'm going to copy and paste it here as well, and that should work. Okay, so now it says what? It failed. Uh, looks like this is pretty far off. On the left it says that the water vapor volume is like what, 78377 times 10 to the minus 5. This is quite different from the critical volume at approximately what, 5.6 times 10 to the minus 5. Okay, so not great, not terrible. Maybe I'll just put what, 25%. Maybe that will work. So it still doesn't match to within 25%. Let's do 30. Okay, so all right, there is some deviation, but it matches to within 30%. Okay, so it's not really great. But it sort of is somewhere in the region of what it sort of predicts in a rather poor manner. It predicts the critical volume of the water. So, but at least we are not terribly far off. It's not like 10 times off. We are in the same order of magnitude, but we should not. In this case, it was not too good. Okay, but you're not too far off. So let's try maybe finding another data point. Okay, what I'm going to do is that I'm going to use a superheated steam as my reference point. Okay, so instead of just a critical temperature, I'm going to use a superheated steam. Okay, superheated steam. Okay, so here's the water critical temperature, pressure, and volume. I'm going to add some things from the steam table. So this, let me go to types, and yeah, let's see. Okay, yeah, the steam tables, let's just have steam at maybe 150 degrees C. Okay, or rather, yeah, superheated vapor, a superheated steam at 150 degrees C, and pressure, maybe you give 0.40 megapascals. Okay, so this is test case 1, super critical point of water. Okay, so test case 2, some superheated steam. Okay, so 0.40 MPa. Okay, P equals 0.40 MPa. Let's do this. Temperature. What should the temperature be? 600 degrees C. 600 degrees C. Let's see whether this works. Oh. It should work. Yes. Okay, let me do types build. I'll just use type swatch. I'm very used to type swatch. Okay. Here are the properties, and the volume here is specific volume here. Okay, V equals to 1.00558 meter cube per kg. Okay, so that's a specific volume. I'm gonna do that again. Okay, so these are the expected behavior. So I'm going to do let water, okay, steam temperature equals to thermal temp new degree Celsius 600.0. Okay. Degree Celsius. I'm going to import that. Steam pressure. Okay, I'm going to do pressure new megapascal 0.40. Steam volume. Okay, this will be specific volume. Okay, so this will be specific volume of new okay cubic meter per kilogram. Kilogram. Okay, cubic meter per kilogram. How much? This will be 1.00558. Yeah, it's a little bit what do you call it? Tedious, but yeah, I guess it's worth it. Okay, let me put a specific volume here. There you go. It's worth it because I can get it correct at compile time, and hopefully it's sort of easy-ish to read. Okay, so let's put the pressure accordingly. So the pressure will be the steam pressure. The critical pressure is the same. Temperature is steam temperature. The rest is all the same. I'm going to change this to PR EOS molar volume. Okay, and the steam specific volume here, yeah, I need to convert it into steam molar volume. Okay, let steam molar volume equals to steam specific volume, and then I need to times something. Okay, so specific volume is in a per kilogram, so I put it to multiply it by the molecular weight. Okay, molecular weight is in grams per mole. So let me do this first. Let water molecular weight equals to molar, let's see, molar mass new gram. Okay, let me see. Molar mass. I'm going to look for molar mass. And let's see what units there are available, if this is the correct one. So it's gram per mole. So I'm going to look at this gram per mole. Gram per mole. Yeah, gram per mole. This is what I have. Gram per mole. And water is just nice. It should be 18.0. And then I'll have to import this. Molar mass, gram per mole. Okay, so the molecular weight is as such. Let's steam molar volume equals to steam specific volume times water molecular weight. Okay, this should take care of the units for us. And I'll change this water critical volume to steam molar volume. And let's get this to within 5% this time. Let's see whether it works. And of course, for the critical properties, I'll have to just do it within 30%. Okay, let's see what cargo watch says. It expects F64, but I found a F32 reference here. Okay. So I'm looking at F32 specific volume and molar mass. Okay, so my imports are messed up. Okay. Okay. Yeah. Let's see. Let's just change this to F64. Okay. Let's remove the all unused imports. Okay. Oh. Wait. Unmerge use. Yeah, I want to just tidy up those imports. Oh, come on. Yes, unmerge use. Okay, come on. Remove unnecessary braces. Quick, quick. I'm gonna delete this unnecessary thing. Let's open tag bar and let's go back to our superheated steam test. Okay, so the superheated steam test is here. And it seems that our Ping-Robinson equation of state molar volume is able to match the superheated steam molar volume, the expected one. So let me change this. Expected steam molar volume. Oh, one more time. Expected. So I'm just renaming this. Okay, and it seems to work. Okay, so let's do it even tighter. See how well this Ping-Robinson equation of state is able to predict the temperature or the volume of superheated steam. Let's do it within 1%. Let's see whether this works. Oh, wow, it really works within 1%. Okay. 0.1. So I'm just going to keep decreasing it until the test fails. Okay. Maybe let's do 0. I just want to see whether... Yeah. Take a look. This actually matches pretty close. On the left-hand side, we have 0.0181. That's the molar volume. On the right, we have 0.0181. Also, it matches to within 0.1%, basically. Maybe let's do 0.01. Okay. So this is 1%, 0.1%, 0.01%. Okay, so that's too small error bound. So I think 0.1% is enough. So yeah, that's how I decided to test my Ping-Robinson equation of state for two things. First, that I test the uh, predicted vapor volume of a superheated steam. Second, I also try to predict the critical volume, but it kind of fares poorly over there. However, what this does show is that at least when it comes to superheated steam, this thing actually works pretty well. Not too bad, not too bad. So this cubic equation of state does work at least for the vapor phase. So I'm just going to save this and call it a day. And I guess I'll see you next time.